Alright everyone, in this video I'm going to show you how to determine if your result is significant with p-values. Why are these p-values important to you as a data scientist? Well, a p-value is used in hypothesis testing to help you support or reject what's called the null hypothesis. Now, the null hypothesis is basically the thing that you're assuming to be true. This is the theory that you assume is correct. It's the status quo. And the smaller the p-value, the stronger the evidence that you should reject this null hypothesis. And typically, this is called the alpha value of 0.05 or less. If we dip below that, we can start to say, yeah, this is probably a scenario where we should assume that the null hypothesis is not true. An example we can use is a coin flip, where we have the null hypothesis of this is a fair coin, and the alternative hypothesis is this is not a fair coin. It's weighted on one side, for example. It's an unfair coin. So an experiment could be we have 14 of 20 flips coming up heads. Now, if we just had 10 of 20 flips coming up heads, well, just intuitively you'd say, well, if there's 50-50 chance of getting a heads, then if 10 out of 20 flips come up heads, that's probably a fair coin. I mean, there's no reason to assume it's not a fair coin, right? What about 11? Well, we're still kind of in the neighborhood of fair coin, but as we get closer and closer to 13, 14, we're starting to wonder, like, that's a lot of heads, you know, someone putting something on the head side to make, or on the other side to make it come up make it come up heads. And in this case of 14 of 20 flips coming up heads, the p-value is 0.115. But if we have 15 heads, then the p-value dips below that 0.05 value. It's 0.0414. With a result less than that, 0.05, we're going to reject the null hypothesis of fair coin. Okay, now let's take a look at some Python code to see another area where we can apply this. So let's say we have two made-up data sets, and each represents test scores from two groups of students, Group A and Group B. Now in our first example, we're going to make both groups the same, basically. And we're going to set the scores to have a mean of 80 and a standard deviation of 5, okay? So looking at this example, we run a t-test comparison of these two groups, right, using the stats, using stats from SciPy. We're going to come up with a t-statistic of 1.3 and a p-value of 0.19. Well, if we have a p-value benchmark of 0.05, this is above that. So these two data, so these two data sets are similar, and we're going to expect their variance to be negligible, which is going to give us a relatively high p-value, and it is. So now let's modify Group B significantly, and we're going to see things shift around a little bit here, right? Okay, so we're going to set the mean to 90 instead of 80. We're going to compare Group A and Group B here. And look at that p-value, 0. So that's completely different, right? So our hypothesis that Group A is different from Group B is satisfied here. And we're going to reject the null hypothesis of B basically coming from the same group of people as A. Now, how far off would you need to have Group B scores to be significant? Well, what if we just used a mean of 81? Here we have a p-value which is 8.9 e to the negative 35. This is very, very small. So that's significant variance. But what if we said 80.15? Okay, now it's lower, but it's not quite 0.05, so we're not going to say that that's different enough. What about 80.25? And here we have a p-value of 0.037. So this p-value meets our criteria of significant at 0.05 or less, so we can say with confidence that as the mean value of Group B starts heading above 80.25, the difference between Group B and Group A becomes statistically significant. So I just showed you an example of a coin flip and comparing Group A and Group B of test scores to use p-values to see whether your result is significant. And hopefully you can see how that works. And thank you very much for watching. Hope you enjoyed it. See you in the next video.